Hello everyone, welcome to this video. In this video we'll be continuing with our third property here. The third property under homomorphism, if we have phi from G to G bar as a homomorphism, right, and G has been taken from the group capital G, then they are saying if the order of this group element G is finite, then the order of the group element phi of G divides the group element, the order of the group element G, correct? So if this is given to be the order of G is given to be finite, let's consider that finite number to be n. So what does it mean? It means that G raised to power n is equals to E, right? So let's mark this as equation 1. Now what we wanted to prove? We wanted to prove that the order of phi of G, this divides the order of G, which is n. So we have to prove the order of phi of G divides n, correct? So now we know that phi carries the identity of G to G bar, so it means that this was our first property, right? So this means phi of E is equals to E. So let's mark this as equation 2. And by the second property, we also know that phi of G raised to power n is equals to phi of G whole raised to power n for all n which are integers. Let's mark this as equation 3. Now we will be making use of property 1, 2 and 3 in order to prove a result, right? So we wanted to see what is phi G raised to power n, right? So you can write E as phi of E using the second result, and then you can write this E as G raised to power n because we know the order of G is n. So according to first equation, it is phi of G raised to power n. Then according to the third result, you can write whole of this thing as phi of G whole raised to power n, correct? So from here you obtain E is equals to phi of G whole raised to power n. Now if this n is the smallest positive integer of such that you have, when you take its power as n you get identity, then definitely n is the order. In that case n would definitely divide n, right? If that is not so, if you have some other integer which is less than n, right, such that phi of G raised to power m is equal to identity, in that case you would have phi m as the order. So in that case also n would definitely divide n. So we thus say that the order of phi of G always divides the order of G. Why it is so? Because n is the n, if it is the order, then it is the least positive integer such that you have this thing. Otherwise it would be some multiple of n, correct? Okay, so this is for this third property. Now moving on to our fourth property, we have to prove that kernel of phi is a subgroup of G, right? This is a very interesting property. So here in this property, we first of all show that kernel of phi, this is a non-empty, right? This is not an empty set. It has at least one element, which is the identity element, because the identity could be written as phi of E according to the property 1. Hence by the definition, this E would definitely belong to kernel of phi. Hence this kernel of phi is non-empty. Now in order to prove that it is a subgroup of G, we take two elements A and B from this subset kernel phi, and we prove that AB inverse is also present in kernel phi. Now if A is present in kernel phi and B is present in kernel phi, it means that phi of A is E and phi of B is also equal to E, right? So now in order to prove that AB inverse belongs to kernel phi, we wanted to show that phi of AB inverse is equal to E. So let's start from here. What is phi of AB inverse? Now because it is a homomorphism, we have operation preserving property, so you can separate out the term phi of A and phi of B inverse, correct? So now because phi of G raised to power n is equals to phi of G whole raised to power n, so you can write phi of B inverse as phi B whole inverse, correct? Now we know what is phi of A. Phi of A is E and phi of B is also equal to E, so you can substitute the values here and simplify, you get identity element. Hence phi of AB inverse is E, hence AB inverse is a member of kernel phi. Correct. So by the one-step subgroup test, this kernel phi is a subgroup of the group G, and this is what we wanted to prove here for the second property. So I hope you understood these two properties well. Well, that is it for this video. Thank you for watching.